An example. Please pause the video and take a moment to read example 12.2 flat tire question mark. Okay, so A, which tire would you choose? Choose one. Would you choose the right front, right rear, left rear? Now, I, as a professor, happen to know that right front is the most popular. If we were in class live, I would actually do this live with the numbers from class, but I'm going to use counts from a past class. So when I asked the class to raise their hands for each of these, 18 people said left front. It was a class of 60 total. Only 6 people said left rear. 25 said right front, and 11 said right rear. Okay. Now, the null hypothesis asserts that my conjecture is wrong and there's nothing special about the right front tire. So it's equally likely to be picked as any other tire. In this case, what would the probability that a randomly selected student picks the right front tire? Now, think about it. How many tires are there? Well, hopefully you saved 4 tires. And we're looking at choosing one. This is still a binary problem. You're like, well, wait a minute, it's not 50-50. Right, but you either choose the correct tire or choose the tire that I'm conjecturing is the right front tire, or you don't. Okay, it doesn't matter which of the others that you choose. It's still, like I said, it's still binary. You either pick the right front tire or not. Now, state the null and the hypothesis. I'm going to do this in symbols and talk about it in words. So the null, in other words, nothing special is happening, and the alternate, my research hypothesis. So the null, they're all equally likely to be chosen. So the red front tire, 0.25. So students pick the right front tire just as often as they would any of the other 3 tires. Now, I'm saying there's something special, that it is more likely to choose that right front tire. So my alternate hypothesis is that students tend to pick the right front tire more often than by chance alone. Now we're going to let X be the number of students in our class who would choose the right front tire. Under the null distribution of nothing special about this tire, what's the probability distribution of X? Well, we've already discussed a little bit. It's binomial in nature, because either you get it correct, you choose the right front, or you don't. And it's 60, and P is 0.25. Once again, I'm using information collected from a past class. So that's where this sample here came from. Determine the exact, from the binomial distribution, p-value. Write out how to calculate this p-value, then use technology. So obviously on an exam, I'm going to not assume that you would have enough technology to do this. But if I do, I know that we're curious how often, how unusual it would be to have 25 or more out of the 60 choose the right front. And when I actually calculate this out, I used an applet to do it. I get 0.0034. That's the exact binomial p-value. So is this p-value small enough to suggest that the class data provides fairly strong or very strong evidence against the null, and interpret the p-value? Well, it's very strong. If you go back and look at that chart, this is a very small p-value. So what am I saying here? I'm saying that if, taking everything as is, that if we just looked at how unusual it would be for 25 or more to choose right front, it would happen only less than, actually, 0.34% of the time. So let's put this, and hopefully this will make more sense as we keep plugging along. Here, interpret the p-value. So if students randomly choose a tire, so any of the 4 are equally likely, it would be very unusual for 25 to pick the right front tire in a class of 60. All right, it would only happen 0.0034. That's the proportion of times it would happen. So that's the p-value. So what do we have? We have very strong evidence, and I list the p-value there, that students tend to pick the right front tire more than 25% of the time. Okay, so there's my summary. My summary is based on that p-value. Now, what if our sample sizes instead had been 4 times as large as it really was? So instead of looking at 25 out of 60, we're now going to multiply both by 4. And we're going to say it's 100 out of 240. Do you think my p-value is going to go up, or is it going to go down or change the same? So we're looking at a much larger class. Remember we talked earlier in the quarter that it's easier to see guessing when you have more questions? Same thing here. It's going to be easier to see that it's an unusual result when you have a larger sample size and, in this case, the same proportion of students who chose the right front tire. So the p-value is going to go down. A smaller p-value provides you more support for the alternate hypothesis, in other words, in against the null. Can we ever find evidence, this is going to come up later, but can we ever find evidence for the null to support that it's random chance? No. Never can find evidence for the null because something else can be going on, all right? So that takes care of this example, and we will be doing more examples with this in note sets 10 and 11.